nanoparticles on such a small scale. So as we change the scale that we're working with, the material properties also change. If we take M&Ms, for example, there are mega M&Ms, regular M&Ms, and minis. So personally, I prefer more chocolate, so I'm going to pick the megas. But if you're a fan of the shell, then you'll pick the minis. Our preference for chocolate and shell dictate which M&Ms we pick. As size changes, the ratio of surface or shell to bulk, the chocolate, changes. This concept is important to materials as well, because the properties of materials change when there are changes in that ratio of surface area to bulk. Nanoparticles are like mini M&Ms. They have a larger surface area to bulk ratio than larger particles do, and this means that properties like melting point, conductivity, and reactivity all change. The properties of nanoparticles make them useful and give them a wide variety of applications, such as improving the display of our devices, protecting our skin from harmful rays, and enhancing drug delivery systems. Another use for nanomaterials is in lithium-ion batteries. The lithium battery industry is experiencing a rapid expansion, as you can see, and it's only predicted to continue increasing in the coming years because lithium-ion batteries are everywhere. Phones, power tools, cars, the International Space Station, you name it. They are so important and revolutionary that in 2019, 3 scientists were awarded the Nobel Prize in Chemistry for their work in the 1970s and 80s on creating these batteries. They found that lithium batteries store 5 times as much energy as nickel-cadmium batteries and 10 times as much energy as lead-acid batteries. Nanomaterials play a key role in the industry expansion because of their importance specifically in the cathode material of the lithium-ion battery. In lithium-ion batteries, the anodes over here are the source for the lithium ions. Lithium releases electrons easily and is the lightest metal, which makes it a good anion. The cathode over here, which is generally a transition metal layered compound, attracts those positively charged compounds, or the positively charged ions. The most successful cathode materials will meet a couple key requirements. They will react rapidly and reversibly with lithium. The material will be a stable conductor that doesn't break down easily. And finally, to make it successful in industry, the material should be low cost and we'd hope environmentally friendly as well. One of the Nobel Award winners, Dr. Whittingham, first used titanium disulfide, like that's in this image, and he used it as the cathode material, but found that the batteries often short-circuited and exploded. And so one of the other scientists decided to substitute titanium disulfide with cobalt oxide because cobalt oxide has a very similar structure, and that battery was a success. The lab group that I worked with chose to focus on batteries with cobalt oxide as their battery cathode material. Cobalt oxide is the layered transition metal compound with lithium closely packed between the sheets of cobalt oxide. So this over here is a TEM micrograph that my group took of the lithium cobalt oxide nanosheets. We know from the work of the Nobel scientists that lithium can be removed electrochemically from these sheets, making it a viable cathode material. Because of this and its compact lattices in the structure, LCO has an advantage in the energy that's stored per unit of volume. This inherent advantage is why the production of LCO batteries has just skyrocketed in the recent past. So once the lithium is completely removed, the structure changes a bit. The cobalt oxide layers rearrange themselves to give a hexagonal plate-like structure like this. The lab group that I worked with synthesized their own LCO nanoparticles to give more control over the starting material, and that's what this image is. This plate-like structure is about 10 nanometers across and 5 nanometers deep. So the lab group that I was working with recognized that lithium-ion batteries are very powerful and will be increasingly important in the coming years. But unfortunately, batteries do not get recycled at high rates. Less than 5% of lithium-ion batteries get recycled in the United States each year. There are many reasons why lithium-ion battery recycling is not a well-established practice. A combination of technical constraints, economic barriers, and logistical issues all contribute to this lack of recycling. Batteries are not designed to be disassembled for our safety, and they also come in a variety of shapes, sizes, and designs, making it difficult to have a one-size-fits-all approach to recycling. So the majority of batteries that are not recycled end up in landfills. And here, the cathode materials can leak from the battery casing and contaminate soils. They can contaminate the soils and groundwater, and this ends up threatening the environment and human health. So with all the LCO that is available to leach into the environment, it's important to study what LCO interacts with once it's in water and soil. So this figure here shows many different possibilities for interaction. Aggregation or dissolution could occur. The structure of the molecules could change from those hexagon plate-like structures that my group synthesized, and they could also interact with salts, natural organic matter, or other molecules in the environment. So the molecular adsorption is where my group focused. We wanted to see if when a molecule adsorbs to LCO, the LCO nanoparticles become more mobile. If they're more mobile, they can leach into our rivers and contaminate our groundwater, like I said. And this isn't good. So we want to track the interaction between LCO and its adsorbed molecule, how well they move together, and if the adsorbed molecule causes dissolution of the LCO. In particular, we looked at phosphate as the adsorbing molecule. We use IR to study where the phosphate attaches, UV vis and dynamic light scattering to see how it moves, and mass spectrometry to see if phosphate aids in dissolution. The group chose to focus on phosphate for several reasons. For one, it occurs naturally in the environment, producing algae in lakes. Also, we're here in Wisconsin, where there is a lot of agriculture, and phosphate is a molecule that's commonly found in fertilizers and can easily make its way into water. Phosphate is also biologically relevant. It's important to repairing bones and teeth, making muscles contract, and helping nerves function also. And finally, phosphate has industrial applications as it's used in engineered coatings. So because phosphate is environmentally, biologically, and industrially relevant, my lab group chose it as a molecule to consider in interactions with LCO. My lab group was investigating how this LCO and phosphate interact. As I mentioned, this includes investigating how phosphate changes LCO's surface structure, its dispersibility, and its dissolution. To determine these three things, we need techniques that are surface focused and can tell us how phosphate and LCO interact. The nanoscale requires that we use techniques that can make highly sensitive measurements. And lastly, we want to know how they interact in the environment. And so it's important that the experiments take place in nature solvent water. It's also important that these experiments occur at environmentally relevant conditions, including concentration and pH, so that our results are applicable to the environment. All right, so here we have our little LCO hexagon plate. It's about 10 nanometers across and 5 nanometers deep. And if we blow up this surface, we see this repeating structure of cobalt and oxygen. This is the surface that our phosphate can bond to. So what we're going to do is communicate with these molecules by looking at how phosphate and oxygen interact through the lens of bond vibrations. We're going to use attenuated total reflectance Fourier transform infrared spectroscopy, or ATR-FTIR for short, and we're going to use that to observe the vibrations that help us learn how the surface structure of LCO changes and when phosphate adsorbs to it. IR spectroscopy gives us those molecular fingerprints of our sample. The bonds between atoms are a little like springs, and weak springs, like this one, absorb low energy light, while stiffer, stronger bonds, like this, absorb high energy light. And so we can identify bonds between atoms by identifying the energy that a bond absorbs. So like I said, ATR-FTIR was used to analyze the lab samples. This is a surface-sensitive technique, which is important for our work, and it monitors surface changes 2 nanoparticles in water, and it allowed us to determine the coordination of phosphate onto LCO. The sample passes up through this peristaltic pump and down onto the nanothin film material. The nanoparticles were spread across a zinc selenide crystal, and phosphate solution ran across the crystal. So IR light coming up from the light source passes through the crystal and interacts with the sample. Some absorption will occur, and light that isn't absorbed can be picked up by the detector. After running the sample, the instrument may give us a spectra that looks something like this. We can use the spacing to learn about the kinds of vibrations and springs that we're dealing with. To understand the data, I'm first showing this cartoon, respecting that it really is a lot more complicated, but it's okay to just approximate the ideas for now as we go over the thought process behind it. So if we take those 2 bonds that we're looking at before, we can figure out which peak may correspond to which bond. We're working with wave number, which is the inverse of wavelength, and so the higher wave numbers will be down here, and that indicates higher energy, while the low wave numbers will be on the right and correspond to low energy. With that information, we can assign the lower energy peak to the slinkier bond and the higher energy peak to the stiffer bond. We can apply what we have here to the spectra that we got when we ran the LCO phosphate through the ATR-FTIR. And this is the spectra that we get. Here there are 8 samples plotted, and this spectra tells us a whole lot about the coordination of phosphate on LCO, but we can learn even more with a little analysis of the spectra. So in this plot, we average those last 8 into this one red solid line. And using curve-fitting software, we deconvolute the peaks so that we could see how individual peaks contributed to the spectra. From these peaks, we determine the coordination of phosphate onto LCO. So the peak around 1150 indicates a POH bend, which means that some of the phosphate on the surface may be protonated. The peaks at 1075 and 1030 are attributed to symmetric and asymmetric O2-PO2 vibrations, while the peaks at 990 and 930 correspond to OPO stretches. Now that we've analyzed the IR spectra, you can kind of put it all together to figure out how phosphate interacts at the surface of LCO. And we can confirm from the IR data that phosphate interacts strongly and irreversibly to LCO at environmentally relevant conditions. We determined that there were 3 main ways that phosphate interacts with LCO. The first is this deprotonated bidentate coordination. We believed that this was the most common coordination of the phosphate onto the LCO. Another coordination is the monoprotonated bidentate, and this one we thought was less common, but is evidenced by that POH bend, and so this shows that POH with the monoprotonated set of oxygens. And finally, we have this outer sphere diprotonated coordination, where we can see that the phosphate is protonated twice. And I'd like to make a distinction really quickly between adsorption and absorption with a B. Adsorption is what we're working with, and that's when particles attach to a solid surface, while absorption is when molecules penetrate into that interior of the solid. So now that we know how phosphate adsorbs to LCO at the surface, we need to figure out how this impacts surface properties. My group focused mainly on the deprotonated bidentate coordination, which is one of these here. And we did that because it seemed to be the most prevalent of the three. So looking at the structure, you can see that there are two negative charges on the oxygens, and so we expect that there will be a decrease in surface charge of the LCO nanoparticles in solution when they're bonded to phosphate. The change in surface charge may allow for electrostatic stabilization of the nanoparticles, and so to investigate this, we measured zeta potential through laser Doppler microelectrophoresis. This measures the movement of charged particles in an electric field. The movement is a function of particle charge, the electric field, and the solvent it's in. My group made 5 solutions with varying concentrations of phosphate. And so they were first measured right when the LCO is added to the solution, and then again after 3.5 hours of sonication. After the second measurement, we see what we predicted. As concentration of phosphate increases, there's a decrease in the zeta potential. Particularly if we look at these last 3 concentrations, 10 to the minus 4 and greater, there's a zeta potential of magnitude 30 or greater, and this magnitude suggests that the LCO phosphate particles are stabilized through electrostatic repulsion. We then turned to dynamic light scattering to see if our observations from the zeta potentials could be backed up by dispersion data. Dynamic light scattering works by exposing the sample to a monochromatic wave of light. The light scatters in all directions, depending on the size and shape of the molecule in solution. A detector picks up the scattered light, and depending on how the intensity of the scattered light changes, we can learn about the molecule's diffusion. One thing that impacts diffusion is size. And so generally, larger particles move more slowly than smaller ones, and so we'd expect the LCO nanoparticles that have aggregated together, we'd expect that they would have a smaller diffusion coefficient, while more dispersed nanoparticles would have a larger diffusion coefficient. Based on the zeta potential data, we were expecting that the LCO phosphate particles would have a larger diffusion coefficient, indicating that they were more dispersed. And this is what we see. So we can see that at the 2 highest concentrations of phosphate, the diffusion coefficient of the equilibrated solutions is greater than the initial measurement. The larger diffusion coefficient suggests that there are smaller nanoparticles in solution, which, when coupled with that zeta potential data, means that increasing the phosphate concentration may cause more stable dispersed colloidal suspensions due to the electrostatic repulsion. And so this image just kind of depicts what's happening. We see when LCO and phosphate are mixed together, we then see phosphate bond to the LCO, and the nanoparticles remain dispersed and they're stabilized throughout the solution. So then we went to UV Vis spectroscopy to track whether or not the LCO phosphate nanoparticles sediment over time. We know from Beer's law that absorbance is proportional to concentration, and so we can use UV-Vis to track the concentration changes. We expect a large absorbance of UV-Vis light when LCO phosphate is well suspended in solution, and then we'd expect the absorbance to decrease when LCO phosphate nanoparticles sediment, because over time, if they sediment, the molecules move to the bottom of the cuvette, and so there will be less LCO spread out throughout the solution to absorb the light. To test this, 3 solutions, each of NaCl or Na2HPO4, were prepared at 3 different concentrations. We know that the LCO solution will absorb UV-Vis light because it is colored, and so the absorbance at 350 and 414 nanometers was measured periodically over 20 minutes, and the difference between those 2 measurements is what we see here. This plot shows that with increasing phosphate concentration, we see a stabilization of the LCO in phosphate, whereas in the sodium chloride solution, there's a clear decrease in absorbance, indicating sedimentation. Our big takeaway from this is that LCO in the presence of phosphate remains in suspension longer than the control. With the ionic strength control, we only have phosphate, and so we'd see this sedimentation at the bottom of the cuvette, whereas when LCO and phosphate interact, we see that stabilization when they bond, and so we don't see sedimentation. After looking at how phosphate and LCO disperse in solution, we looked at how phosphate impacts the dissolution of LCO, or how phosphate makes LCO dissolve into solution. Dissolution is important to study because in some systems, released metal ions are directly responsible for a negative impact on organisms. And so it's important to understand what molecules may influence ion release from the nanoparticles so that we can predict their impact on different ecosystems while the nanoparticles are being produced. The release of lithium and cobalt was analyzed using mass spectroscopy, specifically in inductively coupled plasma mass spectrometry. There we go. ICP-MS allows us to detect most elements at a very low level. The sample gets nebulized, which creates an aerosol, and the aerosol is introduced to a high-temperature plasma, which atomizes and ionizes the sample. A mass analyzer separates those ions based on their mass-charge ratio, and the ions get measured by a detector. My group made solutions of concentrations 0.5 and 50 milligrams per liter of LCO in moderately hard water or moderately hard water with Na2HPO4, which is the red with phosphate on those plots. And at both concentrations of LCO, the solutions with and without phosphate do not have significantly different levels of dissolved lithium or cobalt, which suggests that the phosphate doesn't impact the release of lithium and cobalt from LCO. With dissolution, we weren't totally sure what to expect. More stable and dispersed particles would mean that there's more surface area available for dissolution to occur, but with the phosphate binding to LCO, we may see a kind of protective coating around it that prevents dissolution. So we think that the combination of these things just resulted in a net neutral effect as far as dissolution goes. So through this project, we learned that at environmentally relevant concentrations, phosphate bonds irreversibly to LCO, most commonly in that deprotonated bidentate coordination. This interaction changes the surface charge of LCO and stabilizes it in aqueous solution. It increases the dispersibility and reduces the sedimentation of the LCO nanoparticles. And finally, we saw that at low concentrations, low concentrations and fairly high concentrations for environmental standards, the dissolved lithium and cobalt did not see very different rates of dissolution in samples with phosphate and without. And so this indicates that the stabilizing phosphate contributes to preventing the dissolution of lithium cobalt oxide nanoparticles. These conclusions help us predict what could happen to LCO in the environment once phosphate has adsorbed to it. Because of the increasing dispersibility, phosphate may play a significant role in the transport of LCO in soil and into freshwater environments. So it will be very important in understanding the biological impact of LCO-related compounds. And this is where research is headed next, in determining what phosphate-bound LCO does next in the environment and how it can be retrieved. Retrieval methods are being developed to help protect the environment, as well as to reuse the LCO in batteries to improve the recycling and also reduce the need for new materials. So with that, I'd like to thank the UW-Madison RU program for putting together a great virtual program for us over the summer, specifically Andrew Greenberg and Carrie Phillips, who ran the whole thing, and my group leader, Liz Laudadio. Chemistry faculty and staff members, my advisor Allison, and Graham and Rachel, for just going above and beyond all the time, especially in this past year that has been so challenging. I'd like to thank all my classmates who are here today or not, especially my senior experience group, Cho, Lindsay, and Jojo, for helping me out in the making of my presentation. And then finally, thanks to all my friends and family for all of their support over the years. And thanks to everyone who is here today.